Okay, so this piece is about diffusion, nucleation, and growth. So we're going to start out thinking about diffusion and then how we form microstructures, how they nucleate, how they begin, and how they then grow. So previously we looked at the Scheil solution for solidification in the case where there isn't time for diffusion to happen in the solid. And we said that we typically grow things as dendrites. We found that in the labs. And if we plotted the composition from the first solid to form to the last solid to form, we said we'd have a curve that looked like this. So it would start off quite low, quite pure solid would form first. And then that composition would come up according to the Scheil equation until we got to the eutectic composition, and then the last material formed as a eutectic. And so we'd have a graph of composition versus distance, which at distance would roughly be something related to volume fraction, although it's difficult with the areas and volumes and so on. So then we said that we would want to homogenize this composition by heat treating it so that all of the atoms could interdiffuse and level out this composition profile to the alloy composition. And this happens by a process called diffusion, which you'll study more in 102, but this is the, if you like, the brief introduction to why that occurs. So we consider here, if we take an area, a control area here, sort of projected into the page, and we ask what the flux is, the movement of atoms is through that area, say that's at that position in distance. So we imagine we've got a control area and a flux of atoms going, if you like, through that area. Then in the middle of this composition profile. That amount we call J. So that's a number of atoms in N, say, per meter squared per second. And that's called a flux, the number of atoms going through this control area. So J here is a flux, and it's in numbers of atoms per unit area per unit time. And Fick's first law is the following. So this is a Mr. Fick, and his first law says that the flux is equal to minus a diffusivity times the concentration gradient. So atoms flow down a concentration gradient. So here the concentration gradient is positive. As we've drawn it here, the atoms would move to equalize that, so they would move that way. So they'd move opposite to the concentration gradient. So this dc dx, that's how steep that is. And the steeper it is, the faster atoms would go. And that's a phenomenological law, so-called. So it's one that's true that's observed to be true. It's just an observation. And this D, that's, if you like, the tendency for atoms to diffuse. So it's generally observed that big, heavy atoms, things like tungsten, diffuse very slowly, and light atoms, things like aluminium, diffuse quite fast. And that's a tribute to their diffusivity D. So that's Fick's first law. Now, if we think of atoms as being here as jumping from one side to another according to some thermal activation process, and so it might be possible for atoms to also jump the other way. So we've got atoms jumping forwards and some atoms here jumping backwards. They're, if you like, on a random walk. So that is, the atom might jump here, then it might jump there, then it might jump there, then it might jump there. And net, the probability of jumps this way is greater than the probability of jumps that way. That is, they'll tend to net out to going in that direction. And we would say that the average distance travelled is proportional. If the jumps happen at a constant time interval, then the average distance travelled, which we'll call R, will be proportional to the root of diffusivity times time. And you'll see that in materials physics. So T there is proportional to the number of jumps of jumps. So they happen with the frequency. And d is relating to the distance per jump, classically. Although obviously in atomic lattice that probably isn't quite true, but it's sort of the average distance they move in a jump, or how easy, it probably comes into how easy it is, something like that. And that's, if you like, an atomic view of diffusion. And if we consider instead the number of atoms moving in or out of a control volume, we can derive, and you'll do this in 102, Fick's second law, which is the following. So Fick's second law, which is that the rate of change of composition with time, so the rate at which this composition levels out at this particular point here, say, is equal to d times d2c by dx squared. So it's the second derivative of the composition gradient. So if this is a constant Fick's gradient, that means this has a second derivative of 0, which means that the composition doesn't change with time. But if there's a curvature to it, what this is how is the second derivative, so how fast is that curvature changing, and that gives you the composition change with time. So it's, if you like, the composition flattening rate, or the concentration flattening rate, how quickly a curve like this becomes a curve like this, is proportional to the so this flattening rate here, that's how fast this comes up or this goes down, is proportional to the curvature in the concentration profile, and that's Fick's second law. And you'll derive that by considering the number of atoms moving in and out of a control volume at two different positions. So you'll derive that from Fick's first law. But I'll leave that for 102. Now, if from our atomic view, then diffusion is due to atomic jumps, then we can then think about diffusion and say that the atomic jumps are an Arrhenius effect, something that's proportional to e to the minus q over RT, where q is an activation energy, r is the gas constant, and T is temperature. So this is an activation energy. And that's going to be something like kilojoules per mole, because this is a gas constant, so that's numbers of atoms per mole. If you were to have it in atomic, then this could also be Boltzmann's constant K. And we would say that diffusivity varies with temperature according to some initial diffusivity, when this is 1, that is when it's e to the minus, well, that's e to the naught, so when this has become very big, and then an activation energy Q. And D is, if you like, a constant, and this then is an exponential function. So exponential functions, if you remember, do something like that. And we're taking the negative half, so actually if we flip it around, it does something like that. And we're considering positive temperatures, so we're only considering that end of the graph. And that's what e to the minus q over RT does. And so it's something that gets, have I got that right? It must be getting bigger with temperature, so it's actually it's the other way around, so it's 1 over T. And that's what that would look like. So this D naught then is the diffusivity at 0, or nearly as it approaches 0 temperature. So this diffusivity here is something that varies very rapidly with temperature. So if we homogenize at high temperatures, everything will flatten out quickly, and if we homogenize at low temperatures, it will be very slow. So practically speaking, for instance, in a nickel superalloy, then there's no real point trying to do a heat treatment to homogenize this out at low temperatures, at 600-700 degrees. You need to get up to temperatures like 1,000 degrees, and that's for an alloy that melts at 1,300. So then that's how we would go about taking our ingot that we've solidified and homogenizing it, and the process by which that would happen. And we can do all the calculations for how this would flatten out, which we would do in something like 204. So then the next thing we need to think about is if we have a solid, then how quickly can new phase precipitate out within it? So just to sort of sketch a microstructure, let's see what that looks like. So say we have a phase diagram. So this is temperature, this is composition, and we have a phase, like say it's a eutectic phase diagram, nice simple one. We have a phase alpha here, and somewhere over here there's going to be a beta phase. And say we're here, or no, better yet, say we are here, and we were in the solid alpha phase, so our microstructure looked something like this with alpha grains. And previously, we've said that we would probably nucleate the new beta phase when we came into this alpha plus beta region. When we came into this alpha plus beta region, we went from here in this alpha region to here, then we'd probably start to nucleate the beta phase at the place where there's lots of energy to do that, at the grain boundaries. But if this is at a very low temperature, that might not be possible. You might nucleate new little specks of beta phase within the grains. And probably all of the grains, something like that. And that's how we would then start to form our beta phase. And we can think about that from a thermodynamic point of view, actually, to get how quickly that might happen and start doing some maths to describe that. So we're thinking about what's called the thermodynamic driving force. So if we write the Gibbs energy as being delta H minus T delta S, hopefully starting to get familiar with that equation now, and at the equilibrium temperature, TE, then delta G is equal to 0. So at the phase boundary here. And therefore, delta H at that temperature is equal to T equilibrium delta S. So we can substitute for delta H in here. So delta G as a function of temperature will be then equal to T equilibrium delta S minus T delta S, because we're substituting for delta H in there. And so we can write this as being delta S times T equilibrium minus T. So if we're at a temperature below the equilibrium transformation temperature, this delta T here, then that's equal to delta S times this delta T, this amount here. And that's called the amount of undercooling we have. So this is the supercooling. It's another term that's a synonym for it. So, for instance, if you take very, very pure water that you filtered very nicely so that it doesn't have any bits of dust in it, and you put it in your freezer, you'll find that quite often it won't freeze because, until you go to very high supercoolings, because it doesn't have any nucleation sites. You need the little bits of specks of fluff or dust or particulate in there in order to give it some sites to nucleate from, in order to have an... and if you don't have that, you need a greater amount of energy driving it to produce ice crystals. And quite often in a material, we don't have many places to nucleate things from. But so let's think about that, having done that, having derived an expression for delta G, think about that situation. So we're thinking about a situation, we zoom in on one of those alpha grains in that micrograph, and we think about a situation when you nucleate a little amount, so we're somewhere in a sea of alpha, and you nucleate a little amount of your new phase. And say it's got a radius r here. And say that there is an energy associated with the surface, which is gamma. So you draw gamma like that. So you can draw gamma like that, or you can draw gamma like that. I'll draw it like this. And that's going to be an energy in, if you like, joules per meter squared. It's an energy associated with the surface between the alpha and beta. And we've got an energy available from this supercooling. If we say that's our delta G per unit volume, we've got a thermodynamic energy available from transforming that, of the volume of a sphere, 4/3 pi r cubed, times the amount of it that we've transformed, a delta G per unit volume, and that's an energy that drives it forward, so we'll say that's negative. And we expend that on making this surface. Actually, I'm going to call this surface energy sigma now. Another Greek letter. Sigma is Greek letter S for surface. Sometimes in some other circumstances we call it gamma. It's just terminology. Plus 4 pi, as long as you define it, it's fine. 4 pi r squared, that's the surface area of a sphere, times sigma. And that's our net energy available to grow that. So we'll call that W. And if you graph that out, what you have, I'll actually rub the phase diagram off now. What you have is a graph that looks like this. If we graph W, so this is also going to be a work of transformation. That's, if this was in joules per meter cubed, this is just in joules, against the size of the particle r. So we've got a little particle, and we're asking what W does as we change the size of the particle we're nucleating. So we've got here something that goes off as a minus 4/3 pi r cubed. So that's my minus 4/3 pi r cubed delta GV. And the other component in this equation is something that goes more gently as a squared term. That's my 4 pi r squared sigma. And if I add those two together, well, I get a curve that looks something like this. So that's what W looks like. So what does that mean? Well, it means that for very small particles, things with a small radius r, then actually if you increase them in size by a little bit, by an amount dr, so that's then a radius there of r plus dr. If you increase them in size, say from here to here, from r to r plus dr, then you have to you're spending more energy creating the surface than you're getting from the change in volume. And so that requires energy. It doesn't give you back energy. So that's an unfavorable thing to happen. But beyond this maximum point here, let's call that maximum point a critical radius r star, and it'll have a critical energy W star as well. Beyond that point, the energy you expend on creating new surface is relatively small compared to the energy you expend on the energy you get from transforming from the alpha to the beta phase. And therefore, you need to have a particle of this initial critical radius in order for the transformation to happen. So I'll say that again. So you need to be bigger than the critical radius in order for the transformation to proceed, for an initial nucleus to grow. So if R is greater than R star, the nucleus will grow. And conversely, if R is less than R star, the nucleus will shrink. And we can work out then what R star must be. Yeah. So if we want to find the maximum in a curve, then we just differentiate it. So we can say dW by dr, well, that's equal to minus 4/3 pi r squared times 3. So that's minus 4 pi r squared delta GV plus 8 pi r sigma. Just r squared goes to 2r. And at this maximum point, dw by dr is 0. And at that point, these two things will be equal to each other. So we've got a 0 over here. We pull that over there. They'll be equal. So we've got 4 pi r squared delta gv equals 8 pi r sigma. And we can cancel the pi's. There we go. Gone. And we can cancel the 8 with the 4 and get a 2. And we can cancel the r with the r squared. And then we can say, therefore, that r star at our critical radius is equal to 2 sigma over delta GV. And that's going to be our solution. So this value here is equal to twice sigma divided by delta GV. And we can then go and substitute back in to find out what this value W star is by substituting that back in for R into our original equation. So let's do that over here. So we can substitute back into here. W star, we'll call this W star now, is equal to minus 4/3 pi R cubed. That's 2 sigma divided by delta GV cubed times delta GV plus 4 pi then R squared. So that's 2 sigma by delta GV squared times sigma. And if you multiply that out, then you end up with an answer that's 16 pi by 3 of sigma cubed over delta GV squared, because you see you've got a sigma cubed there, sigma squared, sigma cubed. You've got a delta GV cubed, delta GV, so that's going to be squared on the bottom. This is going to be squared on the bottom. So it all comes out. And so that's our solution for W star. And then we can think about what happens as we change temperature. So as the undercooling goes to becomes very small, as the temperature approaches the transformation temperature, then delta GV here becomes very small. Sorry, there. Yeah, because this term's becoming very small. We have no driving force. And as we go to having no driving force, this work becomes very large and this radius becomes very large. So when we have no driving force, the particle that would grow, the nucleus that would grow, would be enormous. And as we have more and more driving force, smaller and smaller nuclei can come into play. So let me just write that down. So as the temperature tends to the transformation temperature, then delta GV tends to 0. So R star tends to infinity and W star tends to infinity. So what that means, just tidy that up a bit. What that means is that as we have less and less driving force, as we're closer and closer to the equilibrium transformation temperature, then we need bigger and bigger nuclei to be present, and they won't necessarily be there. So what that means is that at small undercoolings, we might not actually see the new phase appear. We need to have some supercooling, some driving force, in order to get whatever nuclei there are there to be able to be effective as nucleation starts to grow new particles. So the other way to look at that is that if we don't have any particles that to nucleate from, then we'll find nucleation quite difficult. And if we put some in, then nucleation become quite easy. There's two examples of that. One is our example with making ice. It's quite helpful often to put a bit of grit in. Basically, you'd require less supercooling. Another example is when you're welding aluminium alloys, quite often people will sprinkle scandium in, or scandium oxide, into the alloy, which provides nucleation sites. And that results in a much finer grained microstructure in the aluminium weld because you have more nucleation sites, so you end up with more grains starting growing when you first form the solid from the liquid. We can keep on going with this. There's one or two last little things to say. I'll just rub this stuff out. We can also imagine that when we precipitate out our particle, what it might do is it might stretch the atomic lattice around it. It might have a larger lattice parameter than that of the surrounding lattice. So imagine different lines in the material would be pushed out as they went through it. So those are imagining different planes, and they've been stretched out by this new particle that has a bigger lattice parameter. And there would be a strain in the surrounding material associated with that. There'd actually be this strain field would extend slightly beyond the particle. And that would then be another term that we could put in. That's a term per unit volume for the sake of argument. And so we could put that in as being a minus 4/3 pi r cubed times a delta GV minus CK gamma squared. I'll explain what those terms are in a second. 4 pi r squared sigma. And here, if we say that the strain is proportional to the composition, so that's the composition, or the composition difference, in fact, of the particle. K is a stiffness constant. K is actually the bulk modulus of your matrix material, of the matrix, sorry. That is of the material around the particle that the particle's nucleating into. And gamma here is then a final term that's to do with the surface. I think. No, it's a shear strain. It's a shear strain. It's an intrinsic shear strain. But it goes per unit volume. And what that means is that you actually have an additional penalty. So what this will do is it will lower this down. So that's plus strain here, plus the effective strain, because it's adding on to this cube term. And so it will lower this down here. Like that. So it's going to push R star bigger and push W star down. So that effective strain will be to make R star goes up and W star goes down. And that will be another thing that makes nucleation harder. So this shear strain, you would need to have then some supercooling to be able to nucleate at all, even from a very small particle. So that's the effective strain. So what does this all mean? What does this all mean? A few headlines. Let's in fact get rid of the maths. It's now a distraction. And this means a couple of things. Generally, having pre-existing particles some things that already exist that you could just grow on will make nucleation easier. And that's called heterogeneous. Hetero, it's Greek, genius. So there's an additional E there. Heterogeneous nucleation. is the name for that phenomena. So that's when you nucleate off of some things that aren't homogeneous, that are distributed, that have a distribution. So if there are some flecks of stuff in your material, in your alpha grain, if you have some particles to nucleate from, then those pre-existing particles will make nucleation easier, which is why we said back at the start that if we had 3 alpha grains, then those heterogeneous nucleation sites would be good places to nucleate new phase. Then we'd be in a slightly different situation. We'd be growing something like a cap, a circle cap or something like that. So that's called heterogeneous nucleation. And what the effect of that is that those will come into play once R star declines to the point that it's smaller than the heterogeneous nucleation sites. So the other way to look at it is that it's sort of an alternative way of thinking about the same thing, which is that they will reduce, there'll be a pre-existing volume, so they will act to reduce R star and W star. And so, and we'll have an Oxford comma, and so we'll reduce the supercooling or undercooling required for nucleation to occur. Okay. Or for precipitation to occur. And the other side of this is that homogeneous nucleation, that is nucleation off of no pre-existing sites, is something that's very difficult. So our observation then would be that because of this thermodynamic argument, homogeneous or homogeneous nucleation is rarely favourable. It rarely happens. And we'll be British about this and have favour with an OUR rather than American. So if we think of an example of this, there's an example actually in aluminium alloys, in aluminium copper alloys. And that's going to be where we'll end this segment, is thinking about this example. So in aluminium alloys, what you observe, or aluminium copper alloys, so these are AlCu alloys, and they're age hardening. How they precipitate out particles that strengthen them, that make them harder as you age it, as you give it time at temperature. So time at some temperatures like 200 or 300 degrees C. And what you find is that the first precipitates you form, so you're in a big aluminium enriched copper grain, then say you're in that grain, then what you form first is a tiny little disc, 1 or 2 atomic layers thick, of the same composition. Sorry, not the same composition, of alternating areas of aluminium and copper, which is called a GP zone. And if you look at the phase diagram, the GP zone doesn't appear on the phase diagram. It then acts as a nucleation site that you can grow another precipitate on, which is called, and so it gets consumed, which is called a theta double prime precipitate. And that also isn't on the phase diagram. It's not the stable phase. Then, but it's this theta double prime is still cubic. It's still the same crystal structure as aluminium. It has a low surface energy, therefore, because it's sharing the crystal structure. And it's got a similar composition to the alloy. And then we go through another one until we finally get to our final theta precipitate. So if you look at the phase diagram, what you see, or look at the Gibbs energy curves, in fact, if you've got your Gibbs energy against composition, so we go from aluminium and it's increasing copper content over here, then we've got our alpha aluminium is doing something like that. Yeah? And say we're in an alloy at our temperature, or our aging temperature, which has a Gibbs energy there. Well, the first thing to happen is it forms a GP zone with an energy, with a composition over here. And so it can lower its energy by forming a tie line like that. And that lowers the overall energy by this amount to give you an overall energy there composed of alpha of this composition and GP zone of that composition. And then what can happen, and this is quite favourable, this doesn't require, because you don't have a lot of surface energy for the GP zone, it's only 2 atoms thick, and it has the same sort of crystal structure as the alpha. So this doesn't have a very big sigma, a very big surface energy that penalises nucleation. So this happens at very low undercoolings, and can happen off of small little lattice defects, interstitials or whatever, vacancies. Then what happens is actually you then form a theta double prime, and that's closer in composition to the final theta phase. And then what happens is the GP zone gets so we went from being here, and the GP zone gets consumed, and the alpha composition here will move to being slightly purer, actually, because you're going down this gradient in the tie line, and you get another bit of energy and forming theta double prime here, and alpha, which of its composition slightly changing. So then you get actually quite a lot more theta double prime forming as well. The volume fraction goes up. And then there's a theta prime, and you get another tie line. And then there's your final theta phase over here, and you get another tie line. And at each step, you get some Gibbs energy. This is for our composition C. So that's sort of what it looks like on your Gibbs energy curves. So what that means is that the phase diagram will look like this. So this is temperature against composition. So this is aluminium, and this is increasing amount of copper in, I don't know, weight percent, atomic percent, whatever you like. That's in degrees C. The copper content, you go from something that's a bit like this. You've got an alpha phase that's there. You've got an alpha plus liquid field, liquid, alpha plus liquid. And your alpha phase is there. There's your eutectic, whatever it is. And this is the alpha plus theta. There's a theta precipitate over there somewhere on the diagram. So you'd have alpha plus theta in the equilibrium phase diagram. But as you go through this sequence, you get a GP zone which comes out initially at a larger composition with a greater amount of solubility in the alpha. So the tie line, it's not in the equilibrium diagram, but the tie line for the alpha GP zone would be somewhere slightly over here. We don't know precisely where it is, but it's somewhere slightly over there. So that's the tie line for the alpha associated with the GP zone. And then the composition of the alpha when it's with the theta double prime, well, it's gone slightly purer. So with the theta double prime, it does that. So that's the theta prime, and that one's the double prime. I always forget the sequence. And then this one would be for your theta double prime. So that's your theta prime, theta double prime, and then this is your final alpha composition for when you're forming with your theta phase. So what that looks like, I'll put a micrograph up here, of the theta prime phase in aluminium copper. And that micrograph shows that you've got little discs, those little outlines you see, those little circles, and you're viewing them either flat on or edge on of those little discs. So you're viewing, it's like you're viewing a, if I find something disc shaped. It's like you're viewing a disc either that way or that way, because there's an orientation relationship with the matrix that's being shown in this micrograph. So if you view the disc like that, you see a circle, and if you view it edge on, you just see a line. And what you're seeing there are circles and lines of the theta prime phase in an aluminium copper alloy that's been aged part way through this transformation sequence. And so that's a way in which aluminium can nucleate the final theta phase with a big surface energy that requires quite large nuclei. And how did it get the nuclei? Well, what happens is first it forms some metastable phase, some phase that's not in the equilibrium phase diagram, but is something that forms during the transformation sequence that's easier to form, that doesn't have as much surface energy. So it's so-called metastable. And that would be the GP zone, and then the theta prime, and then the theta double prime, a sequence of phases, which we'll study in third year in 307. And that's, and you'll do a bit more on it in 204 with MSc 204 with Dr. Van der Perre in second year. But that sort of introduces you to the idea and how nucleation will happen and how we'll form phases in the solid state. So that's been the subject of this segment. And then we can now, having thought about nucleation, we can think about the kinetics of it, how fast it happens. And that will lead us into so-called time-temperature transformation diagrams, diagrams that tell us how long things take to occur. And will also lead us in then to think about steels in the iron-carbon system to finish up this course.